All right, this is a podcast to go over the test that we had on covalent bonding. This is the first question. Which of these molecules has a single covalent bond? Single covalent bond means that there is just one pair of electrons being shared. And in the case of A here, actually, this is a triple bond. B is a double bond. There are two, and then these unshared pairs here. C is another triple bond. It's a lot like the first one. Nitrogen, triple bond nitrogen. And CO is actually going to be probably a double bond, or it could be a triple bond here too. But it's certainly not a single bond. The only single bond for sure is this chlorine bond here. Because remember, chlorine has 7 valence electrons. And so 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. So chlorine only needs to share 2 electrons to make a single covalent bond. So clearly this is the answer right here. Now the shape of the ammonia molecule is actually pyramidal. A pyramidal shape because the unshared pair up here is causing this to go down into like a little pyramid. And see, the bottom of the pyramid looks like this. And these unshared pairs up here are forcing this into a pyramidal shape. Now with the unshared pair, if you included that in the total geometry, this would be a tetrahedral, but because it's just an unshared pair and not something attached to it like a hydrogen, this is not a tetrahedral, this is a pyramidal shape. Which of the following covalent bonds is most polar? Most polar would be the largest electronegativity difference. So if you look on the chart, the answer is going to have to be D, because hydrogen is 2.1 and fluorine is 4.0. See, this is going to be 2.1 minus 2.1, or 0 difference. This is going to be a small amount, probably 0.4 difference. This one could be a little bit bigger, maybe 0.9 difference. And chlorine is about probably 3.0, maybe 3.5 even. Maybe chlorine is 3.0 and 2.1. So see, but the greatest difference is between hydrogen and fluorine. This is like 1.9 difference. So the answer is this is the most polar. The most difference between these numbers makes it the most polar. Only slightly polar covalent. So when you subtract the numbers, it should be between 4 all the way up to perhaps 1 when you subtract the numbers. So this is like 1.9. This is ionic over 2. This one right here is probably in that range. Another ionic, and that's 0. So I'm trying to remember, but I think carbon is like 2.5. Let's make nitrogen 3.0. So see, this is 0.5 difference, which clearly fits in this range here. So the answer is C. Nonpolar means that when you do the subtraction between the numbers, you get 0. So this is a very polar molecule. This is ionic. This is a very polar molecule. This is a very polar molecule also. This is the only molecule that's completely nonpolar, because as we've seen, when you have an element sharing with itself, there's no electronegativity difference here. It's exactly 0. That's nonpolar. Which of the atoms has unshared pairs in its valence shell? So the only one that could have unshared pairs is this oxygen right here. Oxygen needs to show us 8 valence electrons. Just these 2 lines are only showing 2, 4. That means there must be 2 unshared pairs on that oxygen. So the answer is oxygen. So a little balloon over the N represents a pair of unshared electrons, like we've seen before, an unshared pair. What do these all have in common? Well, if you look at the general shape of the electrons in here, they all have a tetrahedral shape. Remember, tetrahedron is when you have 4 things all spread out as far apart as possible from a central atom, and there's no unshared pairs. So these are all tetrahedrons, except when you have unshared pairs, you can't call it a tetrahedron anymore. This is a pure tetrahedron. Tetrahedron having 4 things, 1, 2, 3, 4, attached to the central atom. Now this, because it has an unshared pair, this is actually a pyramidal shape. The water here is, of course, a bent triatomic. But they do have, if you include the unshared pairs, they do have tetrahedral angles in them. Bent triatomic, water, is the bent triatomic. This was actually linear. This is a pyramidal. This is linear, and this is linear. Varipolar covalent. Varipolar covalent means on one side of the molecule, you've got another side of the molecule. One is definitely going to be slightly positive, and one is going to be negative. So, and the varipolar means it's more than just slightly, it's quite a bit. So we're looking for this aspect of, if you divide the molecule down the middle, half of it is going to be electronegative, and then the other half is going to be electropositive. Now that includes the differences between the atoms, but also the shape. If the shape is symmetrical, like for example CO2 is CO2, like this, linear. So linear means it cannot be very polar because the poles cancel each other out. It's linear. This is symmetrical, a tetrahedron. This is the same thing, a tetrahedron, same shape. This is nonpolar. The real answer is water is one of those examples of varipolar covalent. Diatomic molecules mean that when they share electrons with themselves, they do it as 2 atoms. Di means 2. So for example, nitrogen, the total dot structure, there's an unshared pair here. That would be 2 atoms. So really the diatomics are starting with nitrogen, and then oxygen, fluorine, hydrogen also, and then going down from fluorine on the table, chlorine, bromine, iodine, and then I think it's At below. These are the elements here, 1, 2, 3, 4, 5, 6, 7, 8, that are called the diatomics. Obviously, nitrogen here is in that group. So nitrogen is the diatomic. Silicon, aluminum, none of these are actually in this group of diatomics. They all have a formula in nature of like F2, N2, H2. So that's what we mean by diatomic. So this is a very symmetrical molecule. On all sides, it's quite the same. So see, there is a true statement right there. No, asymmetric. See, that's not true. This is not asymmetric. It's not square planar either. It is nonpolar because of its symmetric shape. Again, the word symmetric here to explain this means that you've got a very regular shape all around it. So no part of this molecule is more positive than any other part. So asymmetric means there's no symmetry, which of course is not true. So the answer here is actually C. This is not a polar molecule, and it's certainly tetrahedral, not pyramidal. So here we have various molecules. This is symmetrical, it's linear, that would be not polar. This is also symmetrical. This is a trigonal planar times 2 here. This is a tetrahedral. Again, it's completely symmetrical. And this is a symmetrical molecule. This is asymmetric molecule because, again, this is the planar shape, the pyramidal shape here. So because of these electrons up here, this side is quite negative, and this side down here is quite positive. So D is the polar one. Not diatomic. Well, remember we just went and looked at the various 7 or 8 diatomics. Well, helium is never diatomic. It's always by itself. The rest of these are in the list of the diatomics. let's see, not covalent would have to be something in here as ionic bonding. So that's covalent, 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 covalent. Now you know this is ionic because it has a metal and it's combined with a non-metal. So metal with a non-metal, they're coming from different sides of the table, and that's what we get for an ionic bond. Halogen is group 7A in the periodic table. It means they all have 7 valence electrons. So the halogens are a group in the periodic table, group 7A, that includes fluorine and chlorine and bromine and so forth. You should know them. You should memorize the name of that. Halogens are the group with 7 valence electrons. The trigonal planar basically has 3 things attached to a central atom and no unshared pairs. So this only has 2 things attached. This has 4 things attached, 2 things attached, 2 things attached. This has 3 things attached and no unshared pairs. There's your trigonal planar. Nonpolar. So a nonpolar would be something that's completely symmetric. Well, this is not symmetric. This has a negative and positive side. This is not completely symmetric either because this side is not the same as that side. This is actually not symmetric. This actually is not symmetric because we have this highly electronegative nitrogen and this quite electropositive hydrogen. It's not electropositive. It's just 2.1 versus this is like 3.0. This is actually the nonpolar one because this is, even though it's written like that, this is actually a trigonal planar, and it's quite this is not polar because it's asymmetric. So because this is symmetric, that would make that a nonpolar. So nonpolar, B is the nonpolar one because it has symmetry. It's a linear. This is a bent triatomic, and this one actually is a trigonal planar with a highly electronegative atom out here, which makes this side negative, this side positive. So the nonpolar one in this case is B only. So what makes water polar? Well, water has 2 unshared pairs on the central atom, making this side here electronegative, and this side here is electropositive. So it's the asymmetric shape, and also these bond angles here, these bonds here, have quite a bit of unequal sharing. 2.1, this is like 3.5. So each one of these is a polar bond. So the electronegativity of the bonds and the 2 unshared pairs work together to make water polar. So the symbol above means that there is polarity in this molecule, an unequal sharing. So it's not equal sharing. It's not nonpolar. The electronegativity has to be at least 0.4 here. So that's what this is. Of these groups of elements have the same electronegativity values. Well, the noble gases do because they're all 0, 0, 0. The dot structure for the molecule CO2, you just have to work it out, and there it is. That's the dot structure for CO2. It's the only one that works. So complete the dot structure. We have a single bond here. This is going to be a triple bond. And here's an unshared pair. And that's it. And then use the symbols to show where there's polarity. There is polarity here because this is a highly electronegative atom. It's like 3.0. This one is 2.1. This is an asymmetric molecule because this side is going to be electronegative. This side is going to be electropositive. So in fact, this is electronegative side, and this other part here is the electropositive side. So there it is. That was worth 4 points. The symbols for the polarity of the molecule, you notice that this is an NH3 flipped over on its back, so to speak. These are electrons right here, that's causing this side to be electronegative. Make sure you don't get that backwards. That's the electronegative side. Then going straight through the molecule here to the other side, that has to be the electropositive side. So here we want to put the symbols for water. You notice that's H2O there. So this is the negative side, and if you go straight through the molecule here, that's going to be the positive side over here. So the symbol electronegative, electropositive. Make sure you don't get those backwards. Elements that are likely to be low electronegativity, those are the metals. Metals, like for example, lithium is probably like 1 or so electronegativity. I know sodium, from memory, is something like 0.9. Those are low values. The nonmetals, like fluorine, have like 4.0. These are high values. So the answer is the metals are likely to be the low electronegativity. The only elements with electronegativity of 0 are the noble gases. Examples would be neon, argon, krypton, helium, like that. N2. So think of nitrogen and nitrogen. First, count the number of valence electrons, 5 and 5. We can only put 10 in here total. So since this has 5, it needs to gain 3. So I'm going to bring 3 in from each atom here. That will be the shared electrons. And the other 2 valence electrons, I'll put them over here in the non-shared area. So see, this is actually the dot structure, because now this nitrogen has 2, 4, 6, 8. This nitrogen has 2, 4, 6, 8. Now if you use dots, dots are good. If you're going to use dashes, then don't confuse the two. I don't want to see dots and dashes on the same model. I have to take off points. So dashes are great, but don't confuse them with dots. Make sure you just draw a separate one like this. And of course, oxygen, everybody should know the dot structure for oxygen. The way you figure it out is oxygen has 6 valence electrons and 6 valence electrons for a total of 12 in here. So since it has 6, it needs 2. So I'm going to bring in 2 from each side to share. And then, of course, the other 4 I can put out here as unshared pairs. That would be the answer, 2, 4, 6, 8, 2, 4, 6, 8. And again, like I said before, if you use the dashes, which I'm all in favor of you using the dashes, make sure you clean up the dots so that you don't mix the two, because that would be wrong. So it's either this or it's this, but don't try to make them mix together. Okay, so that's the end of the test. Hopefully this was helpful. Signing off now.